Hello friends, I am Professor Rajnikant working in the Department of Physics, University of Jammu. Uh, First of all, I would like to thank the organizers of this webinar and the convener, the secretary and the entire organizing team for having put in so much of effort in organizing this webinar. I have been asked to speak about, something which belongs to my area of specialization, and I am going to, give you some insights about the relevance of X-rays, which is really a wonderful radiation for the men and the materials. Here, by men does not mean that I have anything against women. It is just to represent the mankind. Therefore, I am using men and materials. Friends, I did my MSc from University of Jammu in 83 and MPhil in 84, followed by PhD. The work I carried out in Radiotherapy Center, Mumbai, as a DA research fellow, and thereafter I went to Oxford University for postdoctoral research work under DST's Boys Cost Fellowship Scheme, and I am working as a full professor for the last 17 years in the University of Jammu, and I am primarily responsible for teaching now for the last over 10 years special and general courses on condensed matter physics to our postgraduate students, and MPhil and PhD students also are being taught by me for their specialized courses. Uh, The topic which I have chosen to demonstrate before you is under the pretext that the audience I am given is the postgraduate research students of physics, chemistry, and biosciences, if I am correct. And I know that if this is the situation, that the audience is from the science backgrounds, medical or non-medical, then this presentation is going to be quite useful to them, I suppose. If first few slides are truly devoted to the development of the concepts of physics, and the second part of my presentation deals with the discovery of X-rays, the third part deals with the applications of this radiation to the materials, and the last part is devoted to the application of X-rays in the field of medical science. So, dealing with the first part, the first half of the 19th century was a period of the development of the exact sciences. The great mathematicians whose names you must have heard, quite common, Cauchy, Euler, Gauss, Hamilton, to name only a few, they laid the foundations for a mathematical quantitative understanding of celestial and other mechanics. Elasticity, magnetism, and optics, etc., including various other concepts of physics, which underwent a huge debate discussion before these were accepted as fundamentals of physical sciences. A series of brilliant experiments were carried out during 1820 to 1830, and it established a relationship between magnetism and electricity. Maxwell's equations were propounded, during 1860, and the equivalence of energy and heat was established by 1850. The basic laws of thermodynamics were also established during the same period. The polarization of light and the hypothesis that light was a transverse wave motion was also discovered during the early onset of 19th century. As a consequence of all these developments, much improved telescopes, microscopes, and other ingenious optical devices were constructed, which helped the mankind to open up new vistas and new regions of analyzing the world of animals and plants apart from the world of humans. The applications of the laws of physics to chemistry and engineering made huge strides, and rational, quantitative, and ever more precise relations, replacing those which were based on vague or unsubstantiated formalisms. Considering the enormous advances in the mathematical description of Mother Nature, some scientists thought that science had reached such a stage of perfection that little more fundamental work remains to be accomplished. It is during this period that the discovery of discharge tube came into being, and it was established that the increasing with the increasing evacuation of the discharge tube, the dark space adjoining cathode gains in length unless it finally suppresses all the luminosity in the gas and reaches out to the glass wall opposite to the cathode, which then shines up into a bright green light called fluorescence. This is how the phenomenon of fluorescence was discovered. Hittorf in Germany and Crookes in London, while investigating this form of discharge, showed that the bright spot on the glass is produced by something, and this something is nothing but a kind of question mark. For this reason, the name of cathode rays was given to this invisible something. If these rays fall on pieces of calcite or fluorite, these minerals glow in beautiful colors, which differ according to the mineral species, that is, the minerals containing different chemical entities. It was therefore observed that cathode rays were a special form of electromagnetic waves, perhaps longitudinal waves, rather than a stream of corpuscles as believed earlier. This view persisted until 1895, when John Perrin in France and J. J. Thomson in Cambridge established electrostatic deflection of cathode rays. By deflection experiments, he also determined the ratio of the charge to the mass of the cathode ray particle, the standard E by M experiment, and found that, assuming the charge to be the same as that occurring in electrolysis, the mass of the particle would be only 1 upon 1800 of the smallest known atomic mass, that of the hydrogen atom. You all are aware of this. So finally, in 1891, on the proposal of Johnstone Stoney, the name of electron was universally accepted for this unit of charge, and its absolute value was determined by a very well-known experiment that is called Millikan's experiment, which was carried out in 1910. Now I take you to the Röntgen discovery without giving you any further detail on the electromagnetic spectrum, because I presume that you all must have read it at the undergraduate level. Therefore, I am going to take you to Röntgen discovery, which started in 1895, and the experiment was carried out by by W.C. Röntgen in his laboratory, and his fiancée also worked in the same laboratory, and they proposed that there is something that is probably flash in his laboratory, and but they could not make out as to what is this was all about. So, in a breathless period of that work, Röntgen convinced himself of the reality of his observations, which at first he found hard to believe. He just could not believe that some phenomena has happened, and when he believed that it has happened, he did not know actually what has happened. So he soon concluded that the fluorescence was actually caused by something, the unknown, that is X, that traveled in a straight path from the spot where the cathode ray in the tube hit the glass wall. That the unknown agent was absorbed by metal, and that these cast a shadow in the fluorescent area of the screen. This X has a academic and emotional quotient attached with the discovery. because by the time he could establish that this is a radiation, and there is nothing known about the properties of this radiation, he wanted to actually put his results in the form of a research publication, but he wanted that experiment to be repeated n number of times before he could conclude that he has found something substantial, and that it is something remarkable which has come to be known to the entire world. So therefore he while carrying out the experiment in his laboratory here, you can see that this happens to be the first X-ray photograph, and which belongs to the right hand of his fiancée. This is the engagement ring which his fiancée was wearing, and this happens to be the first X-ray photograph known to the mankind ever. And when this discovery was made, he, even before publishing his results, he wanted to tell to the world that this cross means that he knows nothing about this radiation. He knows nothing about this radiation. And later on, as gradually the time went by, people observed that X-rays. This telephone is disturbing. I'm sorry, telephone is disturbing too much. The X radiation is a form of electromagnetic radiation, and it has a wavelength of the order of zero point 0.1 to 10 nanometers. Frequency and energy is also given, and these are also at times known as Roentgen radiation. So, friends, this particular experiment which discovered X-rays, for this discovery, Roentgen was awarded the first Nobel Prize in Physics during the year 1902, and it laid a very strong foundation for the development of a new field of science, which now world over is known as the field of X-ray crystallography. Thereafter, the empirical experiments to know the usefulness of this wonder radiation were carried out at various laboratories of Europe and America, and finally came the first ever diffraction method, which was propounded by Max von Laue. This is the first X-ray diffraction technique which is known to the mankind. And during this period, when a lot of experimentation was going on world over, after the discovery of X-rays, William Bragg and W.H. Bragg, both father and son, were also working on the same project, and they discovered that a diffraction of X-rays from a crystal will happen only if the interplanar spacing of the specimen is of the order of wavelength of the incident radiation, that is d of the order of lambda. So therefore this laid a very strong foundation for diffraction physics to come up, and the world received huge applause from the scientists who were working, scientists like Frederick, Knipping, Debye, Scherer, Braggs, Laways. There were so many scientists who were constantly working for the growth of this field. And for your information only, that the year 2014 was celebrated by United Nations as the International Year of Crystallography. And this is a very rare feat. I would like to tell you that such a microscopic or small field of condensed matter physics getting recognition from the United Nations means, volumes of success this field had, achieved. Now, what is X-ray crystallography? Very precisely, I would like to tell you that X-ray crystallography is a method of determining the arrangement of atoms within a crystal. As you all know, that a crystal is nothing but composed of n number of layers in it, and it has a definite volume, shape, and in which a beam of X-rays strikes a crystal and causes a beam of light to spread into many specific directions. When the beam spreads in different directions, then the angles and intensities of diffracted beams can also be recorded. There are two ways to record the intensities. One is the photographic, another is now the digital electronic mode, what we call it as CCD technology, charge coupled device technology. And these, from these angles and intensities, we can produce a three-dimensional picture out of the electron density. You know that, the chemical constitution of any solid is nothing but it is the density of electrons which are contained in it, which are possessed by a crystal. So from the electron density map we can compute different positions of the chemical entities, and atoms can be located. Atoms can be joined together and a molecular structure can be made, and thereafter molecular dynamics can be studied in the unit cell or in the entire crystal structure. This is just to tell you that solid state class of matter is of two types, that is crystalline and non-crystalline. Crystalline is single crystal and polycrystalline, and non-crystalline is amorphous. Single crystal is the one in which we have perfect periodicity and long range ordering, and a polycrystalline means the materials in which the periodicity breaks down at the grain boundaries and it has short range ordering. Whereas in case of amorphous materials, there is no ordering at all. In order to analyze the single crystals and polycrystalline materials, we have various photographic techniques to deal with. For single crystal analysis, we have this Lowes diffraction technique, rotating crystal method technique. Under rotating crystal method technique, rotating crystal technique, we have three different methods. One is oscillation, double oscillation method, then rotation method, and then Weissenberg method. And for analyzing the polycrystalline material, which also is known as a powder material, powder does not necessarily mean that your material specimen exists in powder form. Powder means a kind of small crystallites sitting together, but oriented, each grain is oriented in different direction. Polycrystalline materials can be handled very well by a technique known as Debye-Scherrer technique, and for dealing single crystals for experimentation using CCD technology, we have single crystal X-ray diffractometers, and for dealing with the analysis of polycrystalline materials other than photographic methods, we have powder X-ray diffraction diffractometers, and we computer controlled single crystal X-ray diffractometer technique I am going to speak about a bit, whereas the photographic techniques like Laue method, single oscillation, double oscillation method, rotation method, and Weissenberg method, they are of academic value now these days, because though we have all these experiments working in our laboratory and we have kept it for use of the postgraduate students, so that they can manually handle these equipments, and on their own can see that how actually the in beam is interacting with the crystal, and how the data is being recorded on the photographic plates, and how the cell parameter calculations can be done, and some preliminary basic information about the unit cell can be established. This is a conventional X-ray generator, more than 40 years old, still lying in our laboratory. This is the chiller to cool down the temperature of the X-ray tube. This is the setup, that is Lowes geometrical setup, and this is based on this flow chart. That is, you have a goniometer. On the goniometer, you have the crystal here. Collimated beam of X-ray is coming from the tube and falling on the sample, and this is the flat photographic plate. The distance between the crystal and the film which is contained in this photographic plate camera is capital D, and this is how the diffraction is happening, and the angle with respect to the center of the film is 2 theta, that is diffraction angle. And if you look at the film, when you do this experiment, you get this kind of film. Now we call it as Lowes pattern. This is the center of the film, and this is, you can label these spots as 1, 2, 3, 4, 5, 6, so on and so forth, and presuming that if there are around say 30 spots or so, So you can go from here to here. This is your first spot, this is your second spot, somewhere would be third spot, fourth spot, and so on and so forth. You will have say around 30 spots on this X-ray film. So from center of the film to each spot you can calculate the distance, that is r. So this is r subscript n, where n goes from 1 to 30. And also you know that the distance between the crystal and the film is fixed, that is d. So therefore using this particular formula, it becomes very easy for us to compute the Bragg angle, that is theta. So this is theta subscript n, where n goes from 1 to 30. This r is r subscript n, where n goes from 1 to 30. So we can have 30 values for the diffraction angle. And once we put this value of theta n goes from 1 to 30 in the equation, Bragg's equation, that is 2d sine theta n is equal to n lambda, we can correspondingly calculate the value for dn subscript n. Because if there are 30 diffraction angles, it means that the diffraction is taking from 30 different planes. So dn corresponding to each Bragg angle, we will have 1 d1, d2, d3, d4, and up to dn. So friends, just doing a very small basic experiment for an unknown material whose size would not be more than 0.1 millimeter cube, with the help of X-rays, you have gone inside the crystal and have managed to compute the distance between various planes. This is the beauty of this experiment. So therefore, knowing nothing about the internal parameters, we can compute the diffraction angle and interplanar spacing. Similarly, we can have the rotating crystal method and other Weisenberg method also we can deal with. But looking at the paucity of the time, I think I need to uh, skip these slides, just to tell you in the end that the X-ray crystallography deals with the crystal, the diffraction pattern, and the X-ray structure. These are the three basic steps which are involved in doing the diffraction physics. But it is not as easy as it appears to be, because sometimes the computation of the structure takes months and months together, and still not sure whether we will be able to compute the structure or not. This is the single crystal X-ray diffractometer, which is available in my laboratory as a national facility of DST. And anybody can make use of this facility without charge. We don't charge anybody anything. These are the two chillers which are there to maintain the optimum temperature for the CCD camera and the X-ray tube. So now I move on to the last section of my presentation, that is the aspects of X radiation in the field of medical diagnostics. Friends, medical uses of X radiation is, first the CAT scanning. You also call it as a CT scan. And this CT scan is nothing but this is known as computer axial tomography. This takes care of the three-dimensional view of the internal parameters of the entire human body, and based on this, the doctors can very easily locate the kind of problem you have in the muscle or in the bone. So this technology now has also become quite obsolete, in the sense that we have much better and graded technologies which can be employed for the analysis of bone fractures, dislocations, or ligament fractures. Fluoroscopy is another technique. This is used especially for the people who suffer from arrhythmic heartbeat, and those who have the pacemaker implanted in their body. So what you see that the pacemaker has two leads. Each lead is connected to the upper and lower ventricle of the heart, and it takes around 2 to 3 weeks for the pacemaker to get stuck to the muscle. So during this period of 2 to 3 weeks, it is constant monitoring of the patient is required, and the technique which we use to see whether the leads are still intact with the upper and lower ventricle, we make use of the fluoroscopic technique. Radiotherapy is another X-ray, diagnostic tool which is used for the treatment of cancer patients. And you all know the rigorous after effects of radiotherapy, that people lose their hair, and along with chemotherapy, radiotherapy goes simultaneously. And the dosage, that how long the cancerous area has to be exposed to the radiation, X radiation, it all depends upon the nature and type of cancer and the size of nodule which is present in the human body. uh, this topic, radiotherapy, is also used for ionizing radiation works by damaging the DNA of the exposed tissue, leading to cellular death, and it requires higher radiation energies than the imaging alone. The most useful technique which has come up globally is the technique of mammography. If you look at this particular picture, this is the X-ray picture of the breast of a malignant person, taken with the conventional X-rays. If you look at this, you find a lot of haze over here, and there is almost nothing visible there. So this is the CAT scan of the same breast, and here also it is not possible to see actually where does the nodule lies. But if you take the mammograph, you can very easily see this present over here. And if from the nipple you note down the distance, it is probably few centimeters down that this nodule is present. And early detection of the nodule with the help of mammographic technique can actually make the person get rid of the after effects of radiation and chemotherapy. I mean to say that the person can be treated other than these techniques, if it is stage 1, or even if it is stage 2. So therefore, mammographic technique, this is the setup, and these are the two plates, and here in between these two plates the breast is kept, and it's flattened, so that the nodule also gets visibly seen inside. So I think the meeting is going to be over. So I need to, tell you all that the X-rays are quite bad, in the sense that they also, have damaging effects. And I have given you all my email ID and contact number in on the first slide itself. Anybody who is curious to have some more questions on this particular topic, kindly connect with me. And I would like to tell you that if you go to the libraries, you might have this book on applied solid state physics by Rajnikant. This is published by John Wiley and Sons. And if it is available in your library, please go through this. This is a very wonderful book, and I'm sure you will be benefited with this. And once again, I thank all the organizers for their help, and for the patient hearing of the audience. I am so grateful and happy to be present with you this time. Thank you so much, and please direct your questions to me as and when you feel like. Thank you so much, and have a great time together in this webinar. Stay home, stay safe, and keep the social distance. God bless you all. Thank you very much.